Good morning, everyone. I think we'll go ahead and get started. All the stalwarts, you should get gold stars for last presentation on the last day. Thank you for being here. Great to be with you. I don't know about you. I've thoroughly enjoyed this conference. It's been great to be back with everyone. Thank you for your time. Today, hopefully when you walk out of here, you'll look at this and say, okay, it was worth an hour of my time. Maybe you learned something new. And also maybe there are a few things that you get to look at and reconsider, because we're going to be looking at some things that may go against, things that we've done in this industry for decades. I recently had some vocal cords start acting up, so they've, hopefully today I'll keep them in check, but I apologize if I need to pause for a second. A lot of talking the last couple of days. I won't go through all the course description and all that. What we're going to talk about is what is the impact of air and dirt on hydronic systems. Everyone in this room, to some extent, deals with these systems. Owning, operating, commissioning, maintaining, building, designing. And those of us, I was in the consulting side for a long time as a rep and also as a manufacturer. So like many of you, I've dealt with systems, and more often than not, how often did we see our day-to-day being a combination of wanting to beat our head against the wall and pull our hair out? Because especially those of you who are in commissioning, you go to a job site and your job is to fix all the problems. You didn't design them, you didn't create them, but you have to figure it out. How often do you look around and say, you know what? We have the same problems year after year, project after project. We hear this from customers. I saw it earlier in my career. How many of these things look familiar? Corrosion, fouling of heat exchangers, coils, boilers, equipment that fails. That first year warranty period, or even in 5 or 10 years, when you're commissioning, starting up, how often do you have issues? Data doesn't match. You have air in the system. The contractor has the smallest person on the job site crawling around above ceilings, opening up manual air vents, chasing air, and then all the stuff they damage. You know what I'm talking about. First year, premature boiler failures, and just overall system performance. You look at it and say, new equipment, new job. It's supposedly been purged and flushed, but we're still having the same issues. Some other issues could be air pockets. May sound elementary, but every system starts off dry. The main reason you have high point air vents is to allow the air to be pushed out to make room for the water. Well, we know that not every section of piping, every coil, everything like that is level. So when you fill the system up, you have pockets of air. That's free air. Pumps kick on. Some of those air pockets get stuck. Some become entrained air. That entrained air is messing with pumps, causing pressure gauges to bounce all over the place. How many times do you deal with the low delta T syndrome? How many presentations this conference mention low delta T? And how many of you actually run into that on a regular basis? Especially those that work in humid conditions in the southeast. Design documents show 52-degree discharge air temperature here at 60, 65. Coil is clean. What's going on? Also pumps. I alluded to that earlier. How many times do you get data and it does not match pump curves? I'm sure that never happens, ever. If you have any of these things going on, and likely many of your projects have most of these issues going on, that's money down the drain. And it affects everybody. It affects you because you have to spend more man hours commissioning a job. It affects the engineer, the contractor, it affects everybody. I mentioned it earlier, these are issues that happen all the time. Are they possibly related? And yes, they are. Well, if they are, how are they related? What do they have in common? Think of it this way. It's like the human body. Any of those of you who were able to stop by the Spirotherm booth during the show, you saw a little demo. Circulating fluid, we injected air and dirt into it. That fluid serves everything in the entire system. It's like the human body. If there's an issue with the blood, it affects everything. That fluid touches and affects chillers, boilers, air handling units, heat exchangers. That fluid is the lifeblood of the system. So if I have air in that fluid, it's causing issues. I mentioned it earlier, but I mentioned two types of air in the system. The first air is the free air. That's the air pockets that are in the system. Pump kicks on, those air bubbles are pushed around. That's entrained air. They're along for the ride. The third type is the type that oftentimes we don't think about, and it's overlooked. It's dissolved air. Well, my boss likes to tell me I'm a geek. I guess I am. Let's go back to fluids and heat transfer. Henry's law tells us that fluids and air have a natural affinity for each other. At a particular temperature and pressure, a fluid can hold a certain amount of air dissolved in solution. When air is dissolved in solution, it's very tiny. It has virtually no impact on the chemical or thermal characteristics of the water. However, when it comes out of solution, that's when you have issues. I was doing a presentation several years ago, and someone said, I don't know if I can agree with that or imagine that. And we had some bottles of Coke on the table, and I said, take one and shake it up just a little bit. And I took it and handed him two bottles, one a little shake and one not. And I said, please open those. And he said, I'll open that one, I won't open that one. I said, why is that? He said, it's going to foam. Well, think about it. This is under pressure. The reason you have fizz in those bottles or anything else is carbon dioxide at high pressure. Especially when you shake it a little bit, it activates it. When you crack it open, you'll notice those air bubbles are all throughout the fluid. That gas is coming out of solution. The same way next time you're boiling water, notice where the air bubbles come from. They start at the bottom of the pan where it's hottest. Something to consider, because every system starts off dry, as we talked about. That means you're bringing dissolved air into a system. Well, think about it this way. City, Maine, 60 degrees, 60 psi. Henry's law tells us from our chart that water can hold up to 10.4% dissolved air by volume. Put it in a heating hot water system, what happens? That water goes from being able to hold 10.4% dissolved air by volume to 5.2%. Where did the 5.2% go? It comes out of solution. When an air bubble comes out of solution, it grows 57,000 times in size. Pops out of solution, becomes entrained air, becomes free air, then entrained air. If you have two systems that chilled water or heating hot water, do you typically see that as your nastiest system? All right, think about why that may be. We'll talk about that in a second. But if I'm pulling through a heat exchanger or a boiler, the water comes in at 180 degrees, so right before the suction of the pump, you have all that air coming out of solution, hits the impeller, and it's causing all kinds of things. So what are the negative impacts of air? What's the big deal? We know about corrosion. We know that most folks don't really do a good job of that. It's Joe with a bag of chemicals dumping it in a pot feeder. The other side is that if you have corrosion, you're not only corroding the system from the inside, you're eroding it. Because all that stuff we call dirt, sometimes is dirt. More often than not, it's rust flakes. It's all flaked out. It's in your fluid. It's a liquid sandpaper. It's scouring the system. The other thing is air affects your pump. A pump is designed to pump water only, not compress air and pump water at the same time. The Gould's Pump Manual, Centrifugal Pumps Handbook, and a great white paper by Labor Tabor all reference data that shows just 2% entrained air in the fluid reduces pump performance by 10%. Just 4% air, and I would argue most systems have at least 4%, reduces that pump performance by 43%. Go back to all those pump curves you've seen over the years, and all the times you go, this data doesn't match. Something to consider. The other thing is, water transfers heat about 3,200 times better than air. So, those of you who may have seen the demo, if I have air in a fluid, which most systems do, is that the fluid that the entire system was designed for? No. It's a two-phase flow. It's water and air. Air is an insulator. That 500 times GPM times delta T number that we all use as a check figure, that's 1 gallon of water, 1 degree temperature differential at a 1 GPM flow rate. If I just have 5% entrained air in that fluid, that turns into 475. So, it's very similar to adding glycol to a system. If your customer said, hey, I'm converting my entire chilled water or heating hot water system to glycol, and they went ahead and did it, you would be doing this. Well, this is what's happening. That fluid is affecting every piece of equipment on the system. It essentially derates every piece of equipment because it's not the design fluid. So if you are working with your clients and they're saying, we're having all these issues, we've tried everything, could effective air and dirt removal possibly be a key to that? Yes, it could. Because when you remove air and dirt from your system, you improve the performance of the entire system. You've increased the heat transfer efficiency of every piece of equipment on the job. By doing so, and we'll show you in some case studies, you've allowed those chillers and boilers to work less. Your coils are much more efficient. Think of it this way too. If your cooling coil is several degrees warmer than it's supposed to be, and you're commissioning or testing and balancing a system, you're trying to get the right heat transfer, you have to increase the supply fan to make up for it. So it's causing energy all the way around. So air in the system is basically increasing the total cost of ownership. So how do you effectively remove it? Traditional air separators have been installed since the 60s, but we still have all these issues. So how do we effectively remove air? Well, the first part is we're working with Henry's Law. We want to get that water when it's warmest and its lowest pressure. Almost 30 years ago at Little Red Schoolhouse, I still have my information that shows I want to put my makeup water in at basically that same point that is the theoretical point of no pressure change in the system. That's where you want to put it. So basically, chilled water return before the decoupler on a primary secondary on a heating hot water system, suction side of the pump, discharge side of the heat exchanger or boiler. Several folks stopped by and were asking about, full flow side stream. Well, to be most effective, you want to see all the water all the time. An analogy I discussed with a few folks, and I thought about it a few years ago, was if you're trying to remove like dirt or air from a system, thinking back almost like in a reverse aspect of a bucket, if I have two 5-gallon buckets and I have a really big sponge and a really small sponge, my big sponge can empty the bucket very quickly. The little tiny sponge, it'll take a long time to remove the water. It's almost thinking about the ability to remove air. In most systems, you continually have new water, new air coming in. So if you have a very small separator, yes, it will remove air and dirt, but it may not be able to catch up with all the new influxes. What you want to do too is we're not using centrifugal force to remove anything. We're using gravity. So you want to have the diameter of the vessel about twice the diameter of the inlet and outlet piping, reduce the velocity, suppress the turbulence. In this case, as it goes through the element, you want it to have a nice uniform path. You also want to have the opportunity for bigger air bubbles to have to hit and knock around as they traverse the diameter of the vessel, because that means bigger bubbles, buoyant forces are in play. The same thing happens with dirt particles. It's a separator, not a filter or a strainer, so you want gravity to work. It's also important when you're looking at removing air bubbles. The reason why this is called a coalescing separator is because the tiny bubbles coalesce on the filament. Basically, next time you're in the pool or in the ocean, you see air bubbles collecting on your body underwater. Notice where they collect. More often than not, they collect on the hairs. Bubbles like edges. So as the coalescing media collects them, other bubbles are attracted, and as they get larger, they're able to rise to the top. It's important, too, that if you're removing the air in the dirt, especially on the dirt side, it has to have a path to get out of the unit. So in this case, on the bottom right-hand quarter of that element has a means for the dirt particles to settle to the bottom. There is a manual blowdown valve. You can use automatic and other things to periodically, remove that. The thing that's important too, and again, those who may have stopped by the booth were able to see it on our demonstration unit, is the only way to physically remove entrapped or free air pockets throughout the system is either having an infinite number of air vents everywhere all that air can be caught, or the water has to become absorptive. It has to be some device has to be so effective at removing air that water goes back out into the system and draws those air bubbles back. We can see that in the demonstration unit. We've had a lot of customers over the years. In one case, a unit was installed in a central plant, and they had air issues 1.3 miles away, and it removed air all the way out that far. So, and again, you want to have a media that's going to last. So in this case, it's a copper media, forms a natural tarnish or patina. Units have been in operation for 20 plus years. So you may say, okay, who has used this? Or I don't want to be a guinea pig. Have others done this? Yes, they have. We have, in our case, 1.5 to 2 million units in operation in North America alone over the last 30 years. We'll let you see some of these different factors. This is just a small sampling of some of the results our customers have shared with us. This is not our data. This is what our customers have shown us, that they've picked up plant capacity. They've reduced their delta P by up to 35 psi. We'll talk about that. The other thing is 2 different universities with chiller plants 4,000 and 6,000 tons said that their corrosion coupons on their chilled water system flatlined. So they and some other customers have been able to, in some cases, completely remove rust inhibitor chemicals. You need all the others. The one on the upper right-hand corner was funny. We've seen this, and I know of 4 different instances where it's been installed, and a few weeks later we get a phone call because they think they have a pipe leak because they've had to make up so much water. So yes, it's working and it's effective, but it comes down to the big question of how do you monetize that? Because one of the presentations yesterday, a gentleman did a very good job of talking about we have to write proposals and make, put projects out there in a way that makes sense to not just engineers, but you have to convince the C-suite and everybody in the decision-making process. So how do you put dollars and cents to this? A few years ago, I worked with an energy modeling engineer that I worked with in my consulting days. He and I and some others set off on a way to monetize this. How do you put something together that we can talk all around the country that makes sense? So what we looked at was this, that, and the other, and we decided energy. That's the common denominator. A BTU is a BTU, a KW is a KW. You just pay more or less for it wherever you are in the country. So what we looked at is, at the time, there was no way to model air in a fluid. Nobody had that capability. Any programs out there, you could look at glycol, but that really didn't work. So we said, let's look at energy modeling. We looked at simple payback. That's what we heard all the time. Okay, what's my simple payback? As we looked at it, I said, guys, I was consultant for almost 20 years. I hated it when salespeople came in and they did energy modeling. They changed a bunch of variables, said, trust me, and I didn't know what was behind the black box. So what we did was we took trained trace, we prototyped a 400,000 square foot hospital. We did 12 different iterations for every one because we looked at it and we said we have 2 case studies that have shown 15% increase in chilled water plant capacity after removing air. We've seen pump speed reductions by 22%. That's over a 50% energy savings. We've seen Rochester, New York Housing Authority reduce their gas consumption on an extensive program they did to evaluate this performance of 8%. So we said, let's take a variable and only change one variable at a time. So we wanted to do it too and make sure we were compliant with ASHRAE 90.1. We did it with primary, secondary on chilled water because at the time a few years ago, most existing systems are still primary, secondary. But we said we want to do this and change it so that we have, I think the base for ASHRAE 9.1 was like 0.567 per ton chiller. We added 15% to that. We took the watts per gallon, and that was the only thing we changed. So we changed one variable, did all these different iterations, because I said I want to be able to sit down and evaluate this with anyone who says, show me the data. So we've done that. It's been vetted. There's one ESCO that has a guy who has his PhD in modeling, and he reviewed it and he said, I think it's very, very sound. So we did that. We also wanted to make sure that we were ASHRAE compliant. So the only changes that we made for each building, we basically, we prototyped a hospital. We put it in 5 different cities, and we only made the modifications based on what we needed to do for ASHRAE compliance. The reason we picked part of these 5 cities is, one, there were different climate zones comprised the majority of the United States. Secondly, we had customers. Harvard wrapped up this analysis, flew into San Francisco. They loved it. First question was payback, so he said, do it for us. I'd originally done this for a healthcare system in Nashville, where I'm located. So we ended up with 5 cities, 5 different climate zones. That's where it gets interesting. What they found was when you ran the model and you looked at the energy cost impact, Tampa Hospital had 2 1,430-ton chillers. San Francisco was 2 740s. Nashville was 2 1210s. Boston was about the same size. When I ran the numbers for San Francisco, I was terrified because I thought it's a nice climate. My payback is not going to be there. What we found was because the energy cost is so high in Boston and San Francisco, your paybacks were very, very good. The way we calculated that was, again, after a lot of discussion, was what is the relative premium cost for a high-velocity air and dirt separator over a traditional line-sized air separator. So big impact on chilled water and on heating water, hot water. Simple payback was in years. That's just on energy cost. We had a couple of big contractors in one of my presentations say, I think your numbers are wrong. I said, all right, talk to me. Why is that? He said, I think your payback is faster than that. He said, because if I'm on a retrofit, you're only looking at numbers that are equipment-only cost. A tangential separator requires 2 45s. It takes up twice the length. Your separator is cut the pipe, install 2 flanges. So I said, thank you for that. I still think that's pretty good. So I want to shift to 3 different customers that have a great story to tell that I wanted to share with y'all. One is University of San Diego. Any USD grads out there? Beautiful campus. It's built on a canyon, pretty significant elevation change, as you can see, as it goes up and down throughout the campus. I had an opportunity to meet these folks, and it was before COVID. Very serious about energy, reducing carbon footprint, everything else. And as we met with them, they said, look, we've got a 3,000-ton plant. We know we have air in this system. We have sludge all over the place. We need some help. And they said, okay. So they replaced an existing 20-inch separator with our separator. Steve Glover has been manning and operating that plant since it was built. At the time, 25 years ago, it's now 27 pre-COVID. He was so excited. I went out there right before COVID. He grabbed me by the arm, took me to the central plant, and he said, Stephen, he said, I am operating now with a new normal. I said, okay, tell me about that. He said, my chilled water return pressure always fluctuated between 25 and 60 psi. So we had so much air from all the ups and downs. It's fluctuated for 25 years. We're solid at 60 psi. He said, you've reduced by delta P by 35 psi. He said, that is now I'm getting great heat transfer. He said, the other thing is, on this one building in particular, at the lowest point in the system, he said, that is our sludge factory. He said, I have guys out there every week changing strainers. And he said, it took a few weeks to do it. He said, my entire plant is clean. I'm running better than I ever have. And he said, I'm operating with the new normal simply by replacing the existing air separator and putting in a high-performance air and dirt separator. I've done a presentation in the past where I've named it Creating a New Normal, thanks to Steve. So it really makes a big impact, because those of you who deal with high rises, you know that all that air goes to the top. If you're dealing with campuses or systems that do this, air gets caught at the ups, dirt gets caught at the bottom. This allows it to be removed. And in his case, he said, man, I have freed up manpower that normally we had to have operating. Now this one, I can't tell you where it is or who it was, because we got to come in and help out a customer on a guaranteed performance project. This project was in a small county municipal complex. 3 brand new 200-ton chillers, primary, secondary. We came in after 5 years and they said, please help us. No joke, they said, the contractor who installed the system is in federal prison for fraud, and everything about the system is wrong. They did PVC underground piping, the wrong glue, no thrust blocks, no identification tape, and he said, we've had multiple massive pipe breaks over the years. The only way we know we have them is when the water's shooting up out of the ground or the system fails. He said, we have rocks, chunks of debris, we have air pockets all over the place. He said, we've been writing checks to our customer for like 3 years because we can't get the system to operate efficiently. He said, can you help? He said, we're getting corrosion there. He said, we've got 3 or 4 different technologies in there trying to remove the air and dirt. No, it's not helping. A little small side stream filter was the canary in the coal mine. He said, when we see that thing get all dirty, we know we have another break. And he said, we need help. What can you do? So we went out there and we said, okay, let's put a line size separator in, not a huge system, an 8-inch unit. He said, let's put the 8-inch unit in, chilled water returns, the lowest pressure, highest temperature, put a strainer in with holes that are 3/16 of an inch in size, let it catch all the big stuff next time you ever break, and then let's see what it does. Well, they removed air and dirt from the entire system. He said, what happened is, he said, the next time a chiller went down, they were able to bring the chillers right back up. He goes, we've never been able to do that. He said also, too, that we had to clean the chiller tubes on the evaporator every year or so, if not sooner. He said after 18 months, we opened up the chiller heads and the tubes were clean. This facility, I made more site visits because it was fairly close to where I duck hunt. So during duck season, I got to go see this facility. And I happened to show up when another pipe break happened. This was a small one. It's still unknown where it is. It's been broken for 5 years, and they're still meeting all their energy. They stopped paying their energy penalty. It's clean. It's kind of fun on that one. A third one is Hologic. Hologic is a women's healthcare company headquartered in Massachusetts, but they're out in San Diego, one of their facilities, and they were working with a company that they work with to improve their energy efficiency. They're very intent on reducing water usage, reducing energy usage, and they said, what can we do better? So their partner out there was Willdan Energy Services or Solutions. They're familiar with us, and they said, hey, let's give this a shot. This is one of the facilities, and what we're seeing the last 2 to 5 years has been more and more facilities actually have the data that we need to do a before and after. There are enough data points that you didn't have 10 or 15 years ago. And they said, let's swap it out and let's see what we have. One thing to note is they said we could hear air being removed just little bits at a time over 3 days, and not a huge system, 1,000-ton system. So we had to make up 140 gallons of water from the system. The chart you may find interesting. The blue dots represent, we'll call it year one, with traditional air separation. After they swapped out a traditional separator, put in a coalescing air and dirt separator, you go to the orange dots. What that is chiller output. So you may wonder what's happening. Did the plant reduce its load? What changed in the system? The only change that was made in the system was that the air was removed from the system. Go back to that discussion of, if I have the wrong fluid, it's affecting everything. So here you had a system that had an air-water mixture that was not able to transfer heat as effectively. So in order to handle the same cooling load, your chiller had to produce more tonnage. After the air was removed, they were able to do that. We worked with them, and we had to get them to sign off. They said, yes, we've saved 7.7% energy, and we've raised our chilled water delta T by a degree and a half. So just, 3 examples there. Again, one of the other presenters yesterday, I think, had a really good point. and something that we've tried to adopt and we work with our customers on. I had more time in the office during COVID, and we were trying to have a discussion of how do we help our customers get their projects approved? Because we all know it comes down to dollars and cents, and there are all kinds of decision makers in there. You know, I'm an engineer. My natural inclination is kill them with data. 50 pages, big proposal, you know, give them everything they possibly could. And I would imagine that may be sometimes what you see, but oftentimes people don't look at that. There's a great book that I read that was recommended to me that this is based on. It's called The One-Page Proposal. And I would encourage y'all to get that book. It's really small. But what it does is, and this is actually based on a real document we put together for a customer. We've generalized it, but we've looked at it and said, you need to have something in there that your key decision makers only are going to give you 3 to 4 minutes to read something. And you need to have it so you have the right data and the right information so that technical people, financial people, and just regular folks can look at it and go, okay, that makes sense. So in this case, having that one-page proposal approach allows you to look at it and say, you know, here's what we're trying to do. Here's what our target is. Here are the important snippets of information. Here's a condensed synopsis of what the project is. And then when you get into here, that's where the dollars and cents come into play. I'll show you on the next slide the other thing to look at. Simple payback is a terrible metric. That's what everybody in this industry uses and has for years. It works for some projects, but when you really get to the C-suite and the financial folks, they don't look at it. They're looking, what are my other metrics? So in this case, we want to look at and put it financial. So when somebody scans it, they look down at it. Okay, well, what are some other metrics that make sense as you work with your customers to try to justify your projects? You got to have simple payback because, okay, that's what most people look at. The other thing is, what's your return on investment? You want to look at it and say, okay, if I spend this money now, what's the benefit it's going to give me 10, 20 years down the line? Now, for us, we're fortunate because we have equipment that's been operating for 20 years. So when we can run this analysis, we can actually show a 10 and 20-year internal rate of return, net present value. I know that's, kind of a geek number thing, but money changes over time. And so if you can dial it back to say, my investment now is actually worth this because here's the benefit, that will help make some decisions a lot easier. The other thing is, on this one-page proposal approach, you put financial, you put the status to let that key decision maker know, all right, where are we? I know y'all in commissioning, I used to work with commissioning folks all the time. You're asked to put together, you're supposed to be a third-party reviewer, and you've got you're putting together recommendations that need to be done. And you have to do it without insulting the engineer or making yourself a pariah. So in some way, having a status, helps communicate things. And then the other side is, I think too many times when I, start on the sales side, I realize more often than not, we put information out there and we don't put something saying, all right, what needs to be done? What's the next step? So we have that, and then that's the one-page financial analysis. And if you get into it, if you've got interest rates, financing, discount rates, You can look at 10, 20 years. Like in this case, one of the things that we've liked to look at is, and would encourage all to consider is, if I put, in this case, that was my investment in installing a separator, but you also have energy savings. If you can extend out chiller tubes cleanings, chiller tubes typically are $5,000 to $10,000 a chiller to clean. If you can extend that a year, that's significant. Chemicals, other things like that. So that just gives a little bit different perspective on thinking beyond simple payback of what are some of the real benefits, utility cost, non-utility cost, and maybe even non-bottom line financial ramifications. So kind of wrapping all this up, air in a fluid causes corrosion, and that affects everything. Causes problems, especially during that first year of warranty period. That air and dirt can be effectively removed. You can remove it from an existing dirty system, or put the technology in to keep a system clean from the beginning. Systems that operate free of air and dirt are actually operating the way they were intended to, the way the submittal cut sheets are set up. If they're not operating air and dirt free, removing that air and dirt can allow them to operate with that new normal. And as we just talked about, there are different ways we can look at the financing and number crunching to show those benefits. I appreciate your time and attention, especially the last session on the last day. I think I've got a few minutes. Any questions, comments? Yes, sir. Well, what he said was, say it, and then I'll repeat it back.
Okay, so you have a slide early on called the bottom line simple payback, where you talk about, and it's well back in the presentation.
All right.
I have a question on the slide. It's just a clarification question.
Okay, shoot.
So you said that the simple, so I have a picture of the slide that says at the bottom, yeah, that one right there. So at the bottom it says the simple payback calculations are based on the additional equipment. So in Utah, where we're at, we call that incremental cost. Where, let's say your project is $20,000, but the betterment is $25,000. So
yes.
So the incremental cost is $5,000. Is that what that's saying? Is that the simple payback is based on that incremental cost difference, or the total project cost?
It is the incremental cost. Yes, because as we looked at it, we spent 2 months trying to figure out what that was going to be based on, and we realized if it was installed, Boston's different from rural places. So yes, that's the incremental cost. We have had some folks, we've run numbers with a couple of customers who have found that those numbers, if you look at total installed costs on incremental, it's very similar. Yes. We have units in operation over 20 years. Yeah. Any other questions, comments? No one threw anything, so that's always a good sign. All right. I'll be up here if anybody has anything they want to ask. Thank you for your time. Thanks for being here, and safe travels home. Thanks.